All right, today we're tracking a kind of secret agent, a single pill. We're going to follow its incredible journey from the moment you swallow it all the way to the point where it completes its mission inside your body. Let's get started.
You've probably done it 1,000 times, right? You take a pill for a headache, and a little while later, the pain's just gone. But what's really going on in between? What secret path does that little pill travel to make it all happen? That's exactly what we're about to uncover.
So every journey has to have a destination, and for a pill, that destination is its mission, to create a very specific desired effect somewhere in your body.
Now, the official term for this is the therapeutic effect. This is the whole point of the drug. We're not talking about side effects or anything else. This is purely about the one beneficial thing it's designed to do. It's the entire reason the medicine was created in the first place.
A therapeutic effect could be something as common as pain relief, or it might be more complex, like lowering your blood pressure, calming down inflammation in a joint, or fighting off a nasty bacterial infection. The key is that every pill has a very specific job to do.
Okay, so the pill has its mission, but what if that mission needs to last all day long? I mean, taking a pill every single hour just isn't realistic. This is where the science of drug delivery gets really, really clever.
So, how does that one pill you take in the morning keep on working into the evening? Well, the answer is some brilliant engineering. The pill itself is actually a tiny, time-controlled delivery vehicle. And here's the technology that pulls it off. It's called a sustained-release formulation. You can think of it like a microscopic drip feed system. It's designed to let out its active ingredient not all at once, but slowly and steadily over a long period.
By releasing the drug bit by bit, the amount of medicine in your blood stays at a really nice, consistent level. You avoid that roller coaster of peaks and valleys you'd get from taking multiple doses. And, of course, you don't have to keep remembering to take another pill. It's just a smarter, more efficient way to get the job done.
Okay, our pill has been swallowed, it's releasing its contents, but it's about to hit its first huge obstacle. It's like a security checkpoint or a toll booth that pretty much every drug taken by mouth has to pass through. The liver.
See, before a drug can get to the rest of your body, the blood from your gut takes it on a detour, directly to the liver. And since the liver is your body's main filter, it immediately sees this foreign substance and starts to break it down, or metabolize it. The result? Only a fraction of the original dose ever gets past this checkpoint into general circulation.
This whole process is called the first pass effect, and it's absolutely critical because drug makers have to calculate the dosage knowing full well the liver is going to take a big cut. It's also why some medications, like insulin, can't be taken as a pill at all. The liver would just completely destroy it before it could do any good.
So the portion of the drug that survived the liver is now circulating in your bloodstream. Its next job is to find its specific target, a receptor on a cell, and then interact with it in one of two really fundamental ways. The best way to think about this is like a lock and a key. Receptors on our cells are the locks. Some drugs, we call them agonists, act like a key that fits perfectly and turns the lock, which kicks off some kind of process. But other drugs, antagonists, are more like a key that fits in the lock but doesn't turn. It just sits there, physically blocking any other key from getting in. So an antagonist's job isn't to start a reaction, it's to stop one. By blocking a receptor, it prevents your body's own natural chemicals from causing an effect. This is exactly how many common allergy and blood pressure medications work their magic.
So our pill has found its target and completed its mission, but there's one final, and you could argue most important part of its story. How do we know it's safe? How do we measure that fine line between helpful and harmful?
Well, this isn't just guesswork. There's a very specific mathematical calculation that gives every single drug a safety score. It's a way to actually quantify the risk.
That score is called the therapeutic index, or TI for short. And it's really just a ratio that measures the size of the window between the dose that works and the dose that could become dangerous.
The formula is actually pretty simple. It divides the LD50 by the ED50. The 50 just refers to a statistical midpoint. LD50 is the dose that's lethal to 50% of a test population, and ED50 is the dose that's effective for 50%. This just gives scientists a standardized way to compare risk.
And you can see right here what a huge difference a high TI makes. Drug A has this really wide, comfortable margin of safety between an effective dose and a toxic one. But drug B, it's got a super narrow window, which makes it a much riskier drug that needs way more careful monitoring.
Ultimately, when it comes to the therapeutic index, the crucial takeaway is this.
A bigger number is always better. It's a measure of confidence that the standard dose is nowhere near a dangerous one.
So from defining its mission to engineering a long-haul delivery, surviving the liver's toll booth, blocking a specific target, and finally, proving its safety with a high score, it's pretty clear that a simple little pill is anything but simple.
And that leaves us with a final thought to chew on. We've just mapped out the journey for today's medicines, but what about tomorrow's? As our understanding of the human body gets deeper and deeper, how much more targeted and efficient can these microscopic missions become? It's a really exciting frontier in medicine. Thanks so much for joining me.